Hey, welcome to my introduction to mathematical proofs playlist. We'll be talking about logic. As the name implies, we'll be learning pretty much basic philosophy. So the first thing we're going to talk about is axioms. You might remember this word from the second video, but now we'll actually delve into what this really means. Axioms are rules that are true. We assume them to be true. Why? Well, this becomes a deeper philosophical question, but the idea is this. Math is a tool, and we want to have useful definitions and ways to use them. The ways to use them, these are the axioms. For example, how can you prove that 1 plus 1 is equal to 2? This is actually as simple as it gets, so we just have to define addition in such a way that we're able to use it. Thus, we need to have some things that we can't prove. Let's look at chess, for example. How pieces move are kind of like the definitions. And how you can win the game and the actual rules, like stalemate and checking, those are the axioms. So the tactics and openings that you can develop from this are the actual theorems or the things we want to develop. And it gets kind of confusing because we associate how pieces move with the rules and call both of them rules. But axioms are unchangeable. That's it. You can't change them. But we can add definitions, maybe even change definitions. In our case, if we keep on with the chess analogy, this is adding more pieces that maybe move weirdly. All of this is to say that we come up with simple definitions and rules that we assume without proof that are called axioms. And how we come up with this is a deeper philosophical question. Then we prove theorems from these axioms and definitions. Why am I telling you this? We can only prove theorems from things we already know. That's the main idea. You might even ask, like, okay, what is the original cell, right? What is the foundation of everything that we're building? The axioms are our foundation. We actually have to understand what the building blocks are. We'll introduce the notion of a mathematical statement. A mathematical statement is a statement that is either true or false. An opinion is not a statement. A question is not a statement, so neither of them can be a mathematical statement. And the word mathematical doesn't mean that it's about math, it's just the word that we use to talk about a statement that is either true or false. Then we can prove these mathematical statements, and this is what theorems actually are. And some people like to use the word proposition when we don't know something or we can't prove if a mathematical statement is true or not. So let's consider this mathematical statement: the sky is always blue. Is this true or false? Remember, the word mathematical just means whether the statement is true or false. It's not something that's about math. So if you've been outside, and here's hoping, this is false. But this is still a mathematical statement. At nighttime, the sky would be black. Well, technically, if we specified where and at what time and what range of blue is sufficient, we might be able to make the statement true. Like, for example, the sky is always blue from 2 to 3 p.m. in Iceland. It's very specific, but what about rainy days, right? At this point, we just give up and say that the sky has been blue at least once and get a truthful mathematical statement. Remember, all of these are still mathematical statements regardless of whether it's true or not. So even saying 6 is prime is actually a perfectly fine mathematical statement. We don't need statements to be true. In life, we'll just face problems and not know if it's true or not. So we'll just have to figure it out along the way. And for fun, a cool counterexample. Now, one thing is that some of the ones that are based on English are context based. So for example, what does the word blue mean? Like, you assume that it's just some shade of blue. I'm not going to tell you the exact hex code and then tell you, oh, compare it, right? It's going to be context based, but in math it's more precise. So usually this issue of English meaning different things, they come up in different ways than what do definitions mean, more about how do we interpret the problem. What I actually showed to you guys are two different types of mathematical statements. One is a universal statement, while the other is existential. So universal statements are associated with the words for all, every, stuff like that, where existential is associated with the words exist, there is. So all even plus all even is universal, since we're talking about all even things. And the word universal and existential doesn't matter. It's mainly the idea. You either have to prove something for everything or just something, or one specific case of something. And these are really the two main types of mathematical statements we'll come across and have to use. So formally, we use the word quantifier since we're talking about an object in the statement. We're talking about every even number. So even though I said universal statements, technically the formal name is universal quantifiers. That doesn't really matter. We're going to use both of them synonymously. So in order to prove a universal statement, you need to show it for every case. As if we've seen in a few proofs in the past, we just take an arbitrary element that satisfies all the cases. So if you want to show something about all even numbers, we just take the most general even number or something that represents any even number and then prove it about that. In order to disprove a universal statement, you need to find only one counterexample. Usually the number 1 or the null set are pretty good examples. In order to prove an existential statement, you need to provide an example. And to disprove an existential statement, you need to show that there cannot exist the thing that you're claiming exists. So you have to show that every single case fails. And this is why sometimes existential statements are actually one of the hardest things to prove. Because if you can't find something, how are you going to prove that every single other case fails? Especially if there's an infinite amount of them. And the question, of course, is what does all this have to do with math, right? Describing these things give us a structure and a surefire way to actually tackle these problems. For example, showing that any even number added to another even number is always even, just knowing the fact that it's universal gives us an idea of how we want to do it. Or find a solution, right? Finding a solution, oh, I just need to find a single solution. All we're really doing is adapting English and logic to provide a structure to solve problems. And this is going to give us a really, really good starting point. Or at least that's the idea. Now let's just take a look at a few examples of some mathematical statements. So we'll decide whether it's an existential or universal statement and whether it's true or false. Every prime number is odd. Well, we see the word every, so we're talking about universal. We're talking about everything of one kind, or every prime number. But this is false. Remember, all we need to do is provide a counterexample. In this case, the number 2 is just a nice counterexample. 2 is the only prime number that's even. So, for example, if we change it so that every prime number greater than 2 is odd, then this would be true. Let's look at a second example. There exists a rectangular prism with length, width, height, and all 3 face diagonals that are integer values. So what this means is the width is an integer, the height is an integer, the length is an integer, and on each face, or each distinct side, the diagonal is also an integer. And the triplet 44, 117, and 240 is actually a solution. So there does exist this type of thing. And this is actually called an Euler brick. Some people call it an Euler cuboid. But now, if we add the following restriction, the space diagonals, from one corner of the rectangular prism to the opposite corner all the way on the other side, it passes through the whole entire space, hence space diagonal. If that's an integer, can we still have a solution? Is there something that exists? And we just don't know. This should tell you how hard something like this is, especially this things with there exists. This is existential. It's hard because you have to either disprove every single case or find one. And we've checked up to like a few digits, right? Like 10 digits. It's crazy. And the third one, there exists non-trivial integer solutions for the following equation. A cubed plus b cubed is equal to c cubed. And in this case, non-trivial means no zero value. In the slides, there exists non-zero valued integer. So 0 plus 0 is equal to 0. That's fine, right? But is there anything other than 0 that does this? And no, there isn't. This one only took 400 years to solve. Yeah, it's false. It's called Fermat's last theorem. It's on the shocking side of things. So maybe these last two examples convinced you that understanding how existential and universal statements work is a little important. But before we end this lecture off, we'll introduce a few symbols. So when we're working with math, we like working with symbols because symbols are more precise. So the first one, the upside down A, means for all or for every. It acts as the universal quantifier. So the simplest example is for all x in the real numbers. So this is saying for every value x, that is a real number. And here's an example. So if you try to represent the mathematical statement every integer is prime with some symbols, this is the same as saying for all integers x, or for all x within the set of integers. For every element that is an integer, for every integer, x is prime. And the backwards e means there exists, or for some. And this is the existential quantifier. The simplest example is there exists y in the rationals. Let's look at another thing, turning a mathematical statement from just pure English into including some symbols. So if you say there exists an integer that is prime, or there's a prime integer, this is the same as saying there exists an element in the integers, or there exists an x that is an integer, so that x is prime. And one difficult thing here is translating from English to symbols. This is actually a little bit hard. As you can see in the second example, there's two ways to write out the mathematical statement in English, but one is easier to translate into symbols than the other one is. And if you don't see that, that's perfectly fine. But in my opinion, I think there is one. I'm not going to tell you which one though. And one thing is that the order of quantifiers or statements is actually very interesting. So saying that for all x there exists a y is actually very different than saying there exists a y such that for all x. And we'll just look at a following example, right? We're going to consider the mathematical statement x is a factor of y and x is not 1 or y itself. Then we can add the quantifiers to the beginning of the statement and see what we get. So for the first one, we get that for all x greater or equal to 2, we just say greater or equal to 2 because it makes it easier and it illustrates this point better. So for all x greater or equal to 2, that is an integer, there exists another integer y, so that x is a factor of y, and x is not equal to 1 or y. So for example, if we choose x is equal to 6, well, 18 has 6 as a factor. But then the other way, if we reverse the quantifiers, there exists an x greater than or equal to 2, that is an integer, so that for all integers y, x is a factor of y. So the first one is saying that for all integers x, we can find some integer y so that x is a factor of y. But the second one is saying that there exists an integer x so that for every other integer, x is a factor of every other integer. And this is just not true, right? The first one is true, but the second one is false. So just switching around the order of the quantifiers is very, very different. So be careful when you do this, right? Of course, you don't mean to do this on purpose, and when you're using language or translating, this will happen by accident. But this is always something to be very, very mindful of. So be careful about this. So, just a quick recap. Axioms are rules that we take for granted or rules that don't need to be proved. A mathematical statement is a statement that is true or false. These are the things that we want to prove, and these are what we call theorems. The upside down A means for all. This is a universal quantifier. It talks about every instance or every version of something, so for all x. And the backwards E means there exists, and this is an existential quantifier. It talks about one instance or one version of something, or there exists an integer such that blank. And that's actually it. So, I'll see you in the next one.